Hi, thanks very much for the invitation. Yes, so I'll be speaking about these affine Grassmannian slices and this joint work with a bunch of people, including especially Koa Pham, Peter Tingley, Ben Webster, Alex Weeks, and Odette Kobe. Okay, so let me begin by talking about these affine Grassmannian slices. So we'll start with a semi-simple group, and then we form its affine Grassmannian. So we take G over Laurent polynomials and divide out by G over polynomials. And we have on this affine Grassmannian well-known spherical orbits, so the orbits of the group of G over polynomials. And these orbits are parameterized by the dominant co-weights of our group G. So for every dominant co-weight, I have an element T lambda. So lambda gives us me a map from C star into the affine Grassmannian, or rather into the group G rather. Therefore, a point in the affine Grassmannian, which I denote T lambda. And then I take its orbit under this G of O group, or GT group, and that's called Gur lambda. And these orbits partition the affine Grassmannian. So they can be thought of as kind of, if you're more familiar with finite dimensional flag varieties, they can be thought of as analogs of Schubert cells in the affine Grassmannian. Although they're not technically cells, they're actually kind of a vector bundle over a flag variety. And these Gur lambdas, these are finite dimensional subvarieties of the affine Grassmannian. The affine Grassmannian itself is infinite dimensional. And these guys are finite dimensional. Okay, so that's one family of things we're going to look at, these finite dimensional spherical orbits in the affine Grassmannian. And now we study these transverse orbits of this group G1T inverse. So this means that we work now with a kind of complementary subgroup to our G of O. So we take G in T inverse, polynomials in T inverse, and then this one means that we look for those guys so that when we send T inverse to 0, we get the identity element in the group. So it's if G is some SLN or some matrix group, then these are matrices which are whose entries are polynomials in T inverse and with ones kind of along the diagonal and the constant term 0 everywhere else. And this group is transverse to our group, and we can form these orbits of that group, which will be then transverse. Oops, something bad happened. Sorry. Sorry. Come on. Sorry. That's very annoying. Ugh.
Stop share on reshare usually works.
Sorry? Stop share and share again, maybe. But I gave the talk, so I did this a few times before. I never had this problem. Maybe the... Okay, maybe we're back in business. Come on. Okay, we're back in business. Wait, to you guys it looks normal still? Somehow on my iPad now everything is all messed up.
Looks good to me.
That's good, because on my iPad, stupid iPad is not behaving well. Okay, well, I guess I'll survive. Okay. Okay, well, if it looks good to you, it looks good to me. Okay. Okay. Anyway, here we are. Okay, so we have our, we have our group here, this transverse group, and we form its orbits, which are, I'll denote W mu, and they're transverse to the original Gur lambdas I started with. They're finite codimensional in the affine Grassmannian. And then we can form their intersections, or more precisely, the intersection of Gur lambda bar with W mu. Okay, so this is analogous to in the ordinary flag variety, taking a Schubert variety and intersecting with an opposite Schubert cell. So this results in a finite dimensional affine Poisson variety, usually singular. Okay, now, so just as a quick example of one of these guys, we just take G to be SLN, and I'll pick N times the first fundamental co-weight. So two N's, no coincidence, no accident. And I take mu as 0. And for this special case, I get nilpotent cone of SLN. So I think this maybe was first observed by Lustig, this example. So these guys will be some generalizations of nilpotent cones of SLN. You can't get nilpotent cones of other groups this way, but you can get some nilpotent orbit closures in other algebras, but not the full not the full nilpotent cone. Okay, so these affine Grassmannian slices I've been spending a lot of time on in the past few years, and they have really nice properties. So let me tell you about some of their properties. And most of these properties, well, were developed by these authors or some various subsets of these authors. So Braverman, Finkelberg, and Nakajima, and then this myself with Weeks, Webster, and Jacobi. So the first nice property is that, as I mentioned, it's an affine variety, singular. It carries a Poisson structure. The origin of the Poisson structure comes from a Poisson structure in the affine Grassmannian, which comes from the Mannian triple involving this loop group and this base loop group where it's the algebra. So it's an affine Poisson variety and has nice singularities. It has what's called conical symplectic singularities. In particular, that implies that there's only finitely many symplectic leaves for this Poisson structure. And the formula for dimension is quite simple. It's given by the pairing between lambda minus mu and 2ρ. If this lambda minus mu is not in the positive root cone, then W lambda mu is empty. Another nice property is we have an action of the torus of our group acts on W lambda mu. There's a unique fixed point, which is this point T mu. So T mu is the place where we took the orbit of the group W mu. So it will be contained in there. And within this, so for this action of this torus, we can consider the attracting locus, this torus acting in a Hamiltonian way with respect to this Poisson structure. So this attracting locus is Lagrangian and half-dimensional. And this was, I think, first maybe observed many years ago by Mirkovich. Yeah, I guess I should have added, maybe I should have added Mirkovich to the first list, because I actually think actually the first two things are probably originally due to Mirkovich, Ivan Mirkovich. And the attracting locus actually has a nice description as something that people were interested in anyway. It's the intersection of Gr lambda bar with the semi-infinite orbits S mu. So S mu here is the semi-infinite orbit given by the orbit of the upper triangular group on T mu. So if you were like, so one reason for studying these affine Grassmannian slices, it's a way of taking this locus here and embedding it as a Lagrangian in a nice way inside something that's twice dimensional and carries a Poisson structure. Another nice feature of this affine Grassmannian slice is it carries an integrable system, a complete integrable system. So a map to an affine space of half dimension. So notice this half dimension here, and given by Poisson commuting functions. Okay. The definition of this integrable system is maybe not completely straightforward. We'll see maybe later. But for example, in the nilpotent cone case, in this case up here, it's given by taking the determinants of upper k by k, sorry, not just determinants, but the characteristic polynomials of upper k by k blocks, like upper left k by k blocks of your matrix. Okay. So now comes point 4, which is a sort of new point, and I will come back to this much later in the talk, is that this space W lambda mu has an incarnation called as a Coulomb branch. So this is a theorem of Braverman, Finkelberg, Nakajima, And we'll return to later and talk what this Coulomb branch means, but it's a way of defining W lambda mu, not using this intersection of things in the Affine Grassmannian. So a kind of different way of defining W lambda mu. And it starts with quiver gauge theory. So some data involving a quiver and representations of the quiver. And from that, you can build W lambda mu. So we'll return to that later in the talk. And finally, not finally, another good property, but not the last one, is I mentioned that it has a Poisson structure that was like 0.1 with conical symplectic singularities. And if we have Poisson structure, the affine Poisson variety with conical symplectic singularities, then a theorem of Bazur-Kamnikov and Kaleydin, and then extended by Losev, guarantees us that these varieties have canonical family of deformation quantizations. So a family of algebras whose associated graded is isomorphic to the coordinate ring of our original algebra, original variety. So an algebra whose associated graded is isomorphic to the coordinate ring of W lambda mu as a Poisson algebra. So the existence of this quantization is given by this general theorem that I just mentioned of Bazur-Kamnikov, Kaleydin, and Losev. But in our case of this W lambda mu, we have a very explicit description of this quantization using something called truncated shifted Yangian. So the truncated shifted Yangian is defined as a subquotient of a Yangian. So Yangian is a certain algebra introduced by Drinfeld with generators and relations, the kind of quantum group associated to a loop-Lie algebra, and or maybe to a current Lie algebra to be a little more precise. And then this truncated shifted Yangian means we first form a certain subalgebra of the Yangian, that's the shifted part, and then we take a quotient of that. So it's a certain subquotient of the Yangian. So, but it gives us a very explicit handle on this quantization. For example, this example maybe not coming up here, but for example, maybe I'll write it in. For example, in that case where we got the nilpotent cone, so where W lambda mu is this nilpotent cone of SLN, then the corresponding truncated shifted Yangian is the universal enveloping algebra of SLN modulo central character. And in fact, well, there's a choice of that central character, and in general, there's a choice of parameters in our truncated shifted Yangian, which is anyway dictated by this theorem of Bazur-Kamnikov, Kaleydin, and Losev, which tells us that the parameterization of these quantizations given by H2 of the resolution, or H2 of the partial resolution. Okay, so that's another good property of these affine Grassmannian slices. One thing that's really neat about them, that we have these quantizations that we can really work with in our interest. Okay, and somehow the main reason why I'm interested in these affine Grassmannian slices is because, well, originally this locus is of great importance, I mentioned, because of under the geometric Satake correspondence, there's an isomorphism between its topomology and a representation of the Langlands dual group. So the geometric Satake correspondence gives us this isomorphism, specifically the work of Mirkovich and Vilonin give us this isomorphism. And the irreducible components of this intersection are called Mirkovich-Vilonin cycles. And as I mentioned, this affine Grassmannian slice is something which naturally contains this thing as a Lagrangian. On a slightly related note, a less well-known isomorphism is that if you take the zero fiber of this integrable system, then you get a subvariety of W lambda mu, which contains this Mirkovich-Vilonin locus, but it's bigger, and its topomology is isomorphic to a bigger thing. It's namely this, we take the universal enveloping algebra n minus tensor V lambda and take the mu weight space. So there's also a natural description of its topomology. This will maybe come up a little later in the talk. That's why I mentioned now. Okay. If mu is not dominant, so all this was in the case when mu is dominant. Now, you might say W mu could be defined when mu is not dominant by the same definition. We can still look at T mu inside the Affine Grassmannian. We can still take this orbit W mu, but we'll lose a lot of the good properties. Especially we'll lose the fact that it contains the Mirokovich-Volodin locus. That will be not true. For example, if mu is anti-dominant, then, or if it's equal to W naught lambda, then the intersection of that kind of W mu with GR lambda would just be a single point, and certainly would not contain the Mirokovich-Volodin locus, which would be dense in GR lambda. So if mu is not dominant, we'd like a bigger W lambda mu, one which still has the same formula for its dimension, still contains the Mirokovich-Volodin locus as a Lagrangian, still carries a Poisson structure, and so on and so on. So there is a definition of such a W lambda mu, relatively recent. So here it is. It's a little strange. And it was actually first basically appeared in the work of physicist Bullimore, Demofte, and Gaiato about 5 years ago. So rather than working in the Affine Grassmannian, we work inside just the loop group itself. And we consider matrices which have a Gauss decomposition, or elements of G which have a Gauss decomposition of this form. So where the diagonal part is T mu, and then we multiply by these first congruent subgroups all over the place. And then we define the W lambda mu by forming an intersection like this. And when mu is not dominant, it's not obvious, but not that hard to check, that this agrees with the previous W lambda mu. And for any mu, it has all these good properties which I outlined before. Some of these properties, to exactly make sense of them, you might need to know that the mu is actually a weight of V lambda, but some of them not. For example, like this last property still works even if mu is not a weight of V lambda. As a special case, you can even take lambda to be 0 in this definition. If lambda is 0, then of course this thing is just this GT here. And if lambda is 0, then this W lambda mu is nothing but the, let me write it. So if we take lambda to be 0, then we study W0 mu is nothing but the space of based maps from P1 into the flag variety, G mod B. At a based maps, something like this, maybe. Okay, and which has been studied of degree mu, which has been studied a lot in the work of, for example, Finkelberg and Mirkovich, and Baverman and Finkelberg, and many other people. So in this case, when lambda 0, it's actually just a space of base maps, sometimes called open Zastava space. Okay, and then this, and in that case, this isomorphism here was proven long ago by Finkelberg and Mirkovich. So, yeah, so this space is, even though at first we had mu dominant, even when mu is not dominant, they have this definition which works well. And I should say that, like, this was introduced by these physicists, and then not very long after, I mean, they were motivated by this theory of Coulomb branches. So not very long after, appeared in a more mathematical form in the work of Braverman, Finkelberg, and Nakajima, who gave a more moduli description of this W lambda mu. Okay. Now, in a similar way, we can define Y lambda mu even when mu is not dominant. In fact, it will no longer be a subquotient of the Yangian, but it will still have a similar generators and relations kind of feel to it. And you can work with it just like you work with the case when mu is not dominant. So I mentioned that there's an integrable system back here. So we have this integrable system, and this is valid when mu is not dominant or not dominant. And this gives us a polynomial subalgebra of the coordinate ring. The map backwards gives us a polynomial subalgebra of the coordinate ring of Poisson commuting elements. This can be quantized to a big commutative subalgebra of Y lambda mu, which we call the Gelfand-Cetlin algebra. So should be a lambda on that guy there. So we get a big commutative subalgebra called the Gelfand-Cetlin subalgebra of y lambda mu. For example, I mentioned already that when G is SLN and we take this n times the first fundamental weight for lambda and 0 for mu, then our affine Grassmannian slice was the nilpotent cone, and our truncated shifted Yangian is its natural quantization, the universal enveloping algebra about the center. And then the corresponding, this Gelfand-Cetlin subalgebra, which exists always by quantizing this integrable system, is in this case just what we call the usual Gelfand-Cetlin algebra. Namely, you take centers of all smaller USLKs. So this is made by the collecting together generators of all the smaller USLKs. So it's going to be a big commutative subalgebra, which contains the Cartan, but is much bigger. So.
Could you explain this definition of a W sub mu, where you have a U1, T1? What do they mean?
Sorry. Oh, this definition here?
Yes, please.
Yeah, sorry. Maybe I went over that a little too quickly. So, so here, maybe just let me erase so I have more space. So here, each of these groups are defined like this. Maybe I should have said this. So I can take U. U means the like upper triangular subgroup of my group, like the unipotent radical of L. I take it points over polynomials in T inverse. It has an evaluation map to U given by sending T inverse to 0. And then its kernel is denoted U1 T inverse.
Okay, thank you.
So that's what the U1 T inverse is about.
T1 also means.
And the T1 is the analogous thing, and this is U minus 1. So the analogous thing, but for U minus.
Okay, thanks.
And then I just multiply that stuff together as subgroups inside of the GT T inverse. So maybe, so I don't know how to say it, but like, it's kind of analogous, we're used to thinking in the finite dimensional situation of like things of the form B, W, B minus or something. It's something like vaguely similar to that, but in this affine Grassmannian setting. Okay. Okay, where was I? Yes, so I was saying that we always have this Gelfand-Cetlin subalgebra of our truncated shifted Yangian. And again, in this case, it's just the usual Gelfand-Cetlin algebra. But in any case, it's a big commutative subalgebra. Big means it's it's a polynomial ring whose in the number of generators is half the dimension of W lambda mu. Okay, so we're going to shift gears slightly. And the reason why we're going to shift gears slightly is I'm going to explain a theorem, which we proved a couple of years ago, describing modules for these truncated shifted Yangians, these y lambda mu's. And our description of the category of modules uses as a main tool this klrw algebra. So that's an algebra invented by Kovanov, Lauda, Ruki, and Webster. So some people here are, of course, experts in these guys. It appeared in the talk by Pedro and Gregoire yesterday or the day before. But let me just say a couple words just for those who are not experts. So this is a family of algebras which was introduced by these guys. And the main purpose of these algebras was categorification. So these were algebras introduced such that the category of modules for these algebras naturally carries a categorical action of the Lie algebra, in this case, G check, the Langlands dual of the group we started with. And categorical action which categorifies tensor product representations. Okay, so the input to defining this KLRW algebra, T lambda mu, is the following. We have to choose a decomposition of lambda into a bunch of dominant, well, co-weights, but now we can think of them as dominant weights for the Langlands dual group. And for my purposes, we can just take these lambdas to be fundamentals. So we can always decompose lambda as a sum of fundamentals. Actually, in the actual statement of the theorem, well, okay, I'll come to that in 1 second. let's just imagine they're fundamentals for the moment. And then lambda minus mu, so we have two parameters, lambda and mu. Lambda minus mu is in the positive root cone, so it can be written as a sum of simple roots. So let's call the simple roots appearing there like these, I1 up to IM. So this is, so I1 up to IM will be the list of the simple roots with repetition appearing in this sum here. And then in this klrw algebra, it's an algebra where the elements of the algebra are certain diagrams. And the diagrams look like this. There's red strands and black strands. And the red strands are labeled by these fundamental weights. And the black strands are labeled by these simple roots. So I1 up to IM. And the black strands are allowed to kind of move around and cross, and the red strands are not. And I guess one thing I didn't put in my diagrams, but maybe it's important, is that there's also some dots on the black strands. Okay, so this is a big subject. Maybe, as I said, some people are, there's many people in the audience who are more knowledgeable than me on these guys, but okay. So we proved the following theorem. Let's state it here. So this is with, again, with Tingley, Webster, Weeks, and Jacobi. So we studied the category of Y lambda mu Gelfand-Cetlin modules. So this is the category of modules for our truncated shifted Yangian, such that its Gelfand-Cetlin algebra acts locally finitely. So it decomposes into generalized eigenspaces for this Gelfand-Cetlin algebra. So kind of generalized weight spaces in some sense for this Gelfand-Cetlin algebra. But again, I emphasize this Gelfand-Cetlin algebra is much bigger than the Cartan subalgebra in like this example, for example. So, okay, so we study this category of Gelfand-Cetlin modules for Y lambda mu, and we proved that it was equivalent to the category of modules for this klrw algebra. And here I'm considering the klrw algebra without imposing any condition. So there's sometimes a condition, which is what I denote here. So this is the quotient of the klrw algebra, where I quotient by diagrams where the leftmost strand is black, where at some point the leftmost strand is black, or I guess generated by the ideal of diagrams where the leftmost strand is black, whatever. So if I quotient by that, I get a quotient algebra, which I denote like this. And we proved that that category of those modules is equivalent to category O for this Y lambda mu. So category O for Y lambda mu, it's a category where it's a subcategory of the Gelfand-Cetlin modules, basically where these weights are in some sense bounded above. So just like in kind of the usual category O, and in this example, it coincides with the usual category O. Well, not quite the usual category O, because it's like this business about shifting between generalized central character and generalized weight spaces, but close enough. Pretty much the usual BGG category O. And as I mentioned before, these categories of modules for this klrw algebras were cooked up for the purposes of categorification. So this arrow here means that the Grothendieck group of this category is isomorphic to this thing. So the more well-known statement is that the Grothendieck group of this category is isomorphic to this representation, or okay, so here's where things are getting a little hairy. It's not, in some sense, not really this representation, but more like a tensor product representation. But in some sense, actually, it's actually kind of neither, because the truth is that there's some parameter here, which I've kind of been suppressing in the notation, parameter here, which I've been suppressing in the notation, which in this case is just the central character, which I wrote plus, but you could consider any central character. And when we vary that parameter, it varies exactly what this kind of decomposition, but it varies actually in a slightly, we need some variant of the klrw algebra, which is called the metric klrw algebra. And so it's something even slightly more complicated. And so with different values of this parameter, you can sometimes get the irreducible representation here. Sometimes you can get tensor product representations, and you can also get other representations this way, all of which are classified combinatorially by something called the product monomial crystal. So there's a whole bunch of combinatorics that goes into exactly what representation you're categorifying and exactly what flavor of this KLRW algebra you get here. But for simplicity, let's say we're getting some KLRW algebra and it's categorifying, well, either this or this. And then if we worked with this Gelfand-Selin module instead, we'd be categorifying this kind of representation, which from the viewpoint of let's just move up slightly to here. From the viewpoint of this 6, this is not surprising because these category O modules, they'll be the ones whose singular support will be in this MV locus. So there's a map actually from the growth in the group of the category O modules to this H top here. And there's a map from the growth in the group of the weight modules of these Gelfand-Selin modules to this guy here. So we kind of categorifying what we're kind of expecting to categorify. Well, at least when we're not getting these other representations, but at least sometimes we're kind of categorifying what you might expect. Okay. So that's our theorem from a few years ago. And
can I just ask you, when you say categorifying in the first case in the Gelfand-Selin, do you mean it's a case also where there is a, I don't know, a true representation or something like that, or not quite? It's part of that, or? Yeah,
sorry. Yeah, I should say. In this case, we really get. In this case, we, as you know, we really have a good structure of a two representation. We have functors EIs and FIs, which are bi-adjoint to each other, and so on and so forth. In this case, we don't. We only have, it's only a one-sided categorification. Like there's only FI functors, not EI functors.
Only positive part. Okay. Okay. Yeah. Thank you.
Yeah. Thanks. For example, if you take lambda to be 0, then this algebra just becomes the usual KLR algebra, and you just get the usual statement that modulus of the KLR algebra categorifies U of n minus, but only as a representation over itself. Yeah.
Thanks.
So I should mention, just like to say that this is a good theorem, is that as a corollary of this, you can compute the number of simple Gelfand-Selin modules, because we can study just the size of this the size of this growth in the group of this category, and we can find the number of simple Gelfand-Selin modules for SLN, which was surprisingly actually an open problem, which people had worked on for a number of years and had solved in special cases, but now our method actually gives a general solution. So Ben Webster recently wrote a paper with developing further the combinatorics of this with a co-author, I think a student, but I don't know his name. Okay. So now this kind of goes to sort of to Raphael's question. So we have functors. So I mentioned that here we have this categorifies these guys here, and I have functors. I guess maybe it would be more accurate to call them FI, but anyway, rather than EIs. Anyway, FIs or EIs, but they're not bi-adjoint. We have functors between categories of modules. Well, maybe we have both. They're just not bi-adjoint. Anyway, we have functors between categories of modules for these KLRW algebras. So from these guys to these guys, which are defined the usual business, the usual KLR way. And therefore, because of this equivalence, we get functors on the left-hand side like this. Or if we worked in category O, we would really get the good structure of this two representation with bi-adjoint functors. And the question is, how can we describe this structure purely using the framework of truncated shifted Yangians, and maybe how, or even from and how can we relate it to geometric Satake correspondence? So that's the open problem, which is still open, but I'm going to tell you about some progress towards that problem. Right? Like in some sense, historically, the history of it is first we actually tried to just solve this problem without proving any equivalence like this. But then just trying to construct this functors, I don't know, we gave up and then we just proved this kind of equivalence instead or something. I should say that this equivalence is proved in an extremely hands-on way. Like you take a module here, you do some explicit construction, and you get a module for this algebra by saying exactly how all the generators of these algebras act. And then you go back by doing the same thing. You take the module here and you say how the generators of that algebra act. So it's very hands-on, and this is an equivalence of abelian category. So this is a very explicit kind of equivalence. It does use, though, somehow this Coulomb branch realization, which I'll come to a little later. And it uses, well, it uses quite a few things, but it is very just purely algebraic. Okay, so how can we describe the resulting functors like this? Okay, so now I'm going to switch gears a little bit, and now I'm going to talk about Hamiltonian reduction for Affine Grassmannian slices. So I want to now relate, as a first step to trying to realize, to construct a functor like this, you might try to relate the corresponding spaces. So W lambda mu and W lambda mu plus alpha. How are the spaces related? Right? They're not contained in each other because W mu and W mu plus alpha are disjoint. So a priori, they're not contained in each other. Okay. So, but they are going to be related by a Hamiltonian reduction. So to explain that, we define an action of the additive group on W lambda in a very simple way. So I consider xi of A, that's just the usual like ith root subgroup of G. And A here is just a complex number. And if I want to act on an element in my W lambda mu, I just like multiply on the left by xi of A, take its conjugate, take its class. This actually, if mu is dominant, this just means class in the Affine Grassmannian. If mu is not dominant, it means something slightly more complicated, but it's not very important. And this action is a Hamiltonian action of this additive group, and it has a moment map, so which takes values in C, the algebra of the additive group. Okay, so that's the first piece of structure. And now a second piece of structure is that there's certain maps which we call multiplication maps. And the reason why they're called multiplication maps is because they're just given by basically multiplication in the group followed by the same kind of brackets, the same kind of some kind of reduction kind of quotienting procedure, which I don't want to get into. There is some kind of multiplication maps between these spaces, and they add on the base here. And these multiplication maps quantize to co-multiplication maps, which go in the opposite direction between these Y spaces. So if I don't put a lambda, that means I'm not intersecting with this ger lambda bar or this locus GT T lambda GT bar. And similarly, if I don't put a bar here, it means I'm working with this algebra, which is actually a much easier algebra to work with because it's just a shifted Yangian rather than a truncated shifted Yangian. So it's in the dominant case, it's just a subalgebra of the Yangian. In the non-dominant case, just something with a very nice presentation. It's easy to work with. So these maps here, this co-multiplication maps between shifted Yangians, this studied in a paper with Finkelberg and Pham, Rybnikov, and Weeks from a few years ago. And so recently, this is just on the archive this summer, with Pham and Weeks, we proved the following, that there's a Hamiltonian reduction isomorphism. So if we take our W lambda mu and we use this GA action, so that was a GA action, a very simple GA action I just defined above, and we take its Hamiltonian reduction at level 1. So explicitly, that means we take the inverse image of 1 under the mode map and we mod out by GA, then it gives us W lambda mu plus alpha I. So one reason why you might expect something like this is because there's a theorem of Gannon and Ginsburg, which says that slowed away slices can be obtained using Hamiltonian reductions by unipotent groups. And in the case when of SLN, when lambda is the multiple of the first fundamental weight, then this W lambda mu's are all slowed away slices. Well, slowed away slices intersect the nilpotent cone. And so it's reasonable to see that they should also be related by Hamiltonian reduction involving additive groups or unipotent groups. So in fact, this isomorphism here is actually constructed as a sort of special case or something of a different isomorphism, which is that we work with these, we work here with W lambda mu plus alpha I and W0 minus alpha I. So W0 minus alpha I, mentioned that even when lambda is 0, these spaces are quite interesting. And W0 minus alpha I is nothing but the cotangent bundle of C star. So it's down here. And there's an isomorphism between this product and the preimage of C star under the mode map. And the map from left to right here is an explicit map given by that multiplication map I mentioned earlier. So this is a map we understand very well, and we prove just explicitly that this is an isomorphism, and then it follows pretty readily this statement about Hamiltonian reduction. And this statement here can be quantized to an isomorphism like this, using, again, our co-multiplication map, which quantizes the multiplication map. And on the left side, this W0 at minus alpha is replaced by Y0 minus alpha, which not surprisingly is the differential operators on C star replacing the cotangent bundle of C star. And I should mention that there's not quite a known theorem. It's actually still, this second part is here, still conjectural outside of type A. There's some weaker versions of it which do hold outside of type A. So this is a nice theorem, but unfortunately, this doesn't help us really. At least I don't see yet how it can help us, because it doesn't lead to a functor between categories of Gelfand-Zetlin modules. And the reason is because I mentioned that we have Gelfand-Zetlin subalgebra here. And if we take a look at its image under this isomorphism, we get a kind of, I don't know, mess on the left side. Like the generators of this Gelfand-Zetlin subalgebra don't land inside the Gelfand-Zetlin subalgebra on the left side. So don't quite know what to do. It doesn't help us to make a functor. I mean, I'm not saying it's like impossible that this could work, but at least it doesn't seem, as far as I can tell, it doesn't work. So this was like, well, an interesting fact about the relationship between, so again, we wanted to relate these guys and these guys for the purpose of constructing functors between their modules of Gelfand-Zetlin algebras or modules for category O. And this is a nice relationship. Partially it's nice because there's some very pretty geometry of this Hamiltonian reduction. But unfortunately, this nice relationship doesn't seem to lead to a functor. It doesn't seem to be compatible with these equivalences with the KLRW algebra modules. So we have a slightly different approach here, which does work, but is a bit more complicated. And for this different approach, I have to go into a little bit the theory of Coulomb branches, which is a very nice theory in itself. So maybe it's good to talk about it. So what's this Coulomb branches business about? And it's become, I don't know, hot topic in geometric representation theory, let's say in the past 5 years since the work of Braverman, Finkelberg, and Nakajima. So the input to this theory, so we're changing gears again, new start, is we start with a reductive group. And this is not the same as the group we started with. It's going to be, well, here's an example right here. It's going to be the product of some general linear groups. In fact, generally, it's going to be the product of general linear groups indexed by the Dickin diagram of the group we started with. But in principle, you could take any reductive group and any representation of that reductive group. And physicists say that this defines 3D n equals 4 gauge theory. And this gauge theory has two spaces associated with it, which are called the Higgs branch and the Coulomb branch. And the Higgs branch has a very simple description. It's just the Hamiltonian reduction of the cotangent bundle of V by the group H. And the Coulomb branch, which has a very complicated description, both for physicists and for mathematicians, but fortunately it has a description now for mathematicians. So here it is in one line. So I could spend a whole talk talking about this, but I'll do it in one line. So let's read it from right to left. We start with the stack quotient V over H. So it's like the Higgs branch, but well, we don't double it. So we don't form the cotangent bundle, and we don't take GIT quotient, we take the stack quotient V over H. Then we study a space of maps from this funny curve. So what's this funny curve? Called Raviolo curve sometime. So we take two copies of the formal disk and glue them along the punctured disk. So it's a non-separated curve, looks like a little bubble, sometimes also called a bubble. And we consider maps of this thing into this stack quotient. Explicitly, it means we consider two principal H bundles over the formal disk, which are glued along the punctured disk and which carry compatible sections of the associated vector bundle V. Okay, so that's what the space of maps actually explicitly looks like. And then we take that space of maps it's a big space. It's infinite dimensional, has infinitely many connected components. It actually looks something like a kind of vector bundle over the, well, not vector bundle, but it looks like some kind of space over the affine Grassmannian divided by the action of G of O. Anyway, it has many connected components, which are labeled by the fundamental group of H. And we consider its homology. And we have to be careful about defining this homology because of the infinite dimensionality, but it's possible to define this homology. And because of somehow the gluing of these bubbles together, this homology becomes an algebra, like a convolution algebra, commutative, and in fact, a commutative convolution algebra, and then we take spec of it. Okay, so one line, that complicated definition, that defines something called the Coulomb branch associated to H and V. So why is it relevant to us? So let's return to our situation from the beginning of the talk. We take our group G, we take our dominant weight lambda, we take our mu. So what we do is we start by imagining we're defining the Nakajima quiver variety associated with this data. So we make a quiver, we do some framing that given by lambda. We write lambda minus mu as a sum. We write lambda minus mu as a sum of simple roots, so we write. And then we use the coefficients here to make these guys here. And then we take the H to be the product of these guys here. And this whole thing is like, picture of the Dinkin diagram. And so in this case, GL1 cross GL3 cross GL2. And we take V to be the representation corresponding to the arrows of our quiver. So in this case, it would be Ham C to C to C3, Ham C2 to C3, Ham C3 to C2, and Ham C to C2. So there are two more factors here. And that's our H and V. So if we took this data and we took its Higgs branch, so Higgs branch means we take the cotangent bundle of V, take the Hamiltonian reduction by H, that would be the definition of the Nakajima quiver variety associated with this data. But instead of doing that, we do the other thing, this super complicated thing here, and we form its Coulomb branch. And so Braverman, Finkelberg, and Nakajima proved that this Coulomb branch in this case, so if we start with lambda mu, define the data of H and V in this way, then the Coulomb branch is our W lambda mu, or affine Grassmannian slice. And this works whether mu is dominant or not dominant. And in fact, you could take this to be the definition of W lambda mu when mu is not dominant. And by the way, you can also take this to be the definition of W lambda mu if G is not finite dimensional. So if we start with an arbitrary symmetric Kac-Moody Lie algebra, you can take this to be the definition of W lambda mu. And even if it's only symmetrizable and not symmetric, there's a variant of this Coulomb branch construction due to Nakajima and Weeks, and you could take that as a definition, use that to get a definition of W lambda mu for any symmetrizable Kac-Moody Lie algebra. And every one of these Coulomb branches comes with a canonical quantization, which I'll call maybe AHV. And if you go back to the definition, it's just, you just take C star equivariant homology everywhere, and you get a non-commutative algebra. And in that case, in this quiver case, it produces you this truncated shifted Yangian. Okay. So again, I meant, let's just back up for 1 second. So to recall the goal. So our goal was we had these equivalents between these modules for y lambda mu and klrw modules. On the klrw side, we had functors which categorify an action of our Lie algebra. We want to see those functors on the side of our y lambda mu's. And now we're going to see them by some general machinery of this Coulomb branches, turns out. And so that's why for introducing the Coulomb branches. So then we're continuing in the Coulomb branch framework and with the following general construction. So given any H and V, then another piece of data, which is just a map from C star into H, there's going to be two algebras we're interested in. One is the Coulomb branch algebra, so this non-commutative Coulomb branch associated to H and V. And the second is, well, two other groups. So, or sorry, a group, another group, and a representation. So the other group is LC, which means the Levy subgroup associated to Xi, so which is simply the centralizer of the image of Xi in H. We'll assume that Xi lands in the maximal torus of H. So then this is the Levy subgroup. And the second is the invariance in V for the action of Xi, for the action of this C star. So that's a representation of that LXi. So that's the pair, another pair are interested. And we proved that these two algebras are in some sense related by a version of the of Hamiltonian reduction. So it's not simply Hamiltonian reduction. It's some like more complicated relation, but it's morally like a kind of Hamiltonian reduction. It's how you get from this algebra to this algebra. But it leads to a functor between modules, Gelfand-Cetlin modules for the first algebra and Gelfand-Cetlin modules for the second algebra, a functor which is actually quite easy to study. Okay, so unlike the actual Hamiltonian reduction I talked about earlier, which didn't lead to a functor, this, like, I don't know, more complicated business does lead to a functor. And here's a, so now we're going to apply it to our situation. So we're going to take H and V so that the Coulomb branch is W lambda mu. Again, that means that these are quiver gauge theory. So H is some product of GLs associated with the Dickin diagram. V is some Homs between vector spaces associated to the framed Dickin diagram. And we take the other piece of data C, so it's a map from C star into this group H. What is it? Well, I'm going to pick one of the GLs, one of the vertices of my Dickin diagram, I, and consider the map of C star into GLVI, just the simplest thing you can imagine, just put like this guy in the top left corner of the matrix. So that, like, its centralizer is easy to see. It splits off. So most of the GLs are unchanged. And just the GLVI is split off into, well, this part and this part. So GLVI minus 1 cross C star. So it splits the GLVI into these two factors. And so all this part together is like the related to the quiver where you've reduced the ith vertex by 1. And reducing the ith vertex by 1, that's like increasing the mu by alpha I, because lambda minus the mu is controlling the dimension of the ith vertex. So the Coulomb branch associated to this new theory is just the product of this guy with this W0 minus alpha I, which, remember from before, is an uninteresting factor. It's just the cotangent bundle of C star. And it comes because actually it comes from just this C star alone here. It's Coulomb branch of C star with the trivial representation is the cotangent bundle of C star. So, so this theorem here tells us whenever we do this kind of we call this kind of a parabolic restriction or something. Whenever we do this parabolic restriction of Coulomb branches, we get a functor like this. And so we get a functor in our case because this guy is obtained as the Coulomb branch algebra associated to this theory here. And therefore, we obtain a functor. So we're just going to kind of ignore this factor. It turns out to not be important. Therefore, we're going to get a functor between categories of Gelfand-Cetlin modules here from y lambda mu to y lambda mu plus alpha I. And on the right-hand side, we have a functor between modules for these KLRW algebras defined in the usual KLR way that I mentioned before. That was the functor we were interested in, that we liked because it give us our categorification. Again, one sort of like a one-sided categorification in this case, and a proper categorification if we pass the category O on the left side. And this diagram commutes. So this is the functor defined using this Coulomb branch kind of machinery and this sort of complicated version of Hamiltonian reduction involving the Coulomb branch. And so this diagram commutes. So now we've sort of partially succeeded in our goal of understanding this functor on the left side. I say we only partially succeeded in our goal because we really wanted to relate this this thing to the geometry of the and Grassmannian slices and hopefully relate it to the geometric syntactic correspondence. And we still don't know how to do that because this functor here came in this kind of Coulomb branch way, and we understand it well algebraically, but we really don't understand that well the geometry of it. So we haven't completely succeeded in that way. Okay, and that's it for my talk.
Okay, let's thank Joe for a great talk. So any questions for Joe?
Can I ask a question? So you were mentioning Gans Ginsburg. So so the construction you have at the end, does it contain as a particular case, maybe even projecting on category, I don't know, the actions you get on say rational Cherenkov algebra modules of type A? Does your construction generalize that? And I mean, because in this case, for example, if you think of the point of view of Hilbert spaces, the induction restriction the functors, whatever, yeah, are not very geometric either. So is that similar?
Yes, I think, I mean, at least, I'm not an expert. Ben is far more the expert on this part, but yeah, at least Ben says, yes, it does generalize the functors of like, of Beznikov and Eddinghoff. Is that the functors you're referring to?
Exactly. So they're not geometrical. If you think of them, if you think of rational Cherenkov algebras, they are fairly, this functor of Eddinghoff and Kamnitzer, they are fairly natural functors. But from the point of, they rely on the hyperplane geometry, things like that. But from the point of view of Hilbert schemes, if you think of your Cherenkov algebra as a quantization of a Hilbert scheme of points on C2, then that's weird. What you're doing is weird. I mean, anyway, it's just not that it's weird, but it's just that there is no definition in this setting.
Yeah, so it's similar in our case. I mean, yeah, so maybe we shouldn't expect some geometric exact version. Maybe
No, one expects something, one would like something like that. So no, continue, please. We would like to have that in the Cherenkov case. So.
Yeah, I guess I should have maybe, that's a great point then, Raphael. But maybe I should have mentioned, like, maybe from the very beginning or something, that, in geometric representation theory, or say in this part of geometric representation theory, we have these affine Grassmannian viewpoint and this quiver variety viewpoint. And the quiver variety viewpoint, the action of the Lie algebra comes by kind of explicit correspondences. And then it's easy to quantize those to functors because you just quantize those correspondences to bimodules and they give you functors. But when you work with this affine Grassmannian viewpoint, then the action of the Lie algebra is kind of described not explicitly, comes by this Tanakian formalism. So you don't have any explicit correspondences to work with. You don't have a place to like get started to quantize and build your functors. So that's kind of what makes the business hard and why you kind of don't expect any, simple way of building the functors. But nonetheless, we would like to relate it back to the geometric syntactic.
Your Coulomb branch stuff brings it back to quiver variety land.
Sorry?
But the Coulomb branch stuff brings it back to quiver variety land.
In some ways, it's a way of kind of harnessing what we see in the quiver variety land and importing it into the Affine Grassmannian slices. Yes.
So what you say about actions or this whatever, these functors being very very different nature on either side of the duality. I mean, is it if you decategorify, is it somewhat similar to this SL2 that I don't know if it's Kamnitzer who promoted that, or that you would see either as coming from Lefschetz or from monodromy actions? I mean, does it similar to that?
In the simplest case of this Affine Grassmannian business, like for SL2, the action of the E's comes by this Lefschetz operator and the cohomology of these Gur lambda bars. Yeah. or rather on the intersection homology of these Grad lambda bars. Yeah.
So there is one case is class of hyperplane section, and in the other case that would be more like on the other side more like a monodromy action. Or can you see that, or is it not really?
I don't know about monodromy action. On the other side, it's well.
Maybe Jordi, maybe Jordi can comment on that. Actually, he knows these things better than me. So.
I think Raphael's just talking, like, you know, in this mirror symmetry business is that Lefschetz the Lefschetz operator gets exchanged with a monodromy, like a Picard-Lefschetz SL2.
Oh, but that's more like the two-dimensional mirror symmetry, like the usual mirror symmetry, not this kind of symplectic duality mirror symmetry, three-dimensional mirror symmetry, I think. I mean, I think there's like duality of, or some, which is called Higgs-Coulomb branch duality, or symplectic duality, or 3D mirror symmetry. And then there's the ordinary mirror symmetry, two-dimensional mirror symmetry. And maybe this exchange of the Lefschetz with the monodromy thing has to do with two-dimensional mirror symmetry. I'm not sure.
So in your Hamiltonian reduction statement, does that kind of mean that I should, so I could imagine like trying to understand these slices by like starting at a simple one and then progressively moving in like an alpha string. And are you kind of saying that what I do at each point is take a cotangent bundle of C star and then compactify it in some complicated way and then repeat?
Yeah.
Like, so,
Yes. Yeah. Or you know, you can go in the opposite direction too, which maybe, but yeah, if you're going outwards and starting with simple ones, then yes, each time you multiply by the cotangent bundle of C star and then compactify it. I don't have much to say about the compactification step, so I don't know how helpful it is, but yeah, there's but yeah, another so for example, like in the special case of SL2, I should say it's not like in the special case of SL2 when lambda is 0, then this corresponding like W lambda mu is something like when this Toda system, I'm not really an expert on this, but this is a bit more of what I learned from Finkelberg, is a kind of Toda system. And then this business with the isomorphisms we have is like building some kind of, I don't know what they call it, but some lax matrices description of the Toda system. So there's like some like classical kind of integrable systems kind of stuff, which is a special case of this.
Are there any other questions for Joe? If no, let's thank Joe again.
Okay, thank you for listening, everyone.
Okay.
Can I ask one more question, Joel?
I have questions.
So like I've always been fascinated by this picture, like that, I guess I'm not sure, I guess it's Finkelberg-Merkovich picture, kind of that if you fix the difference of lambda and mu, then in some sense but then you make it more and more dominant, then in some sense this thing has a limit. Yeah. And in general it's much simpler, like the the case in SL2, you kind of take C2 mod mu n and you let n go to infinity, and then the limit should just be C2.
Exactly. Yeah. Yeah. You get this in general. You get this closed Astava space as the limit.
And I guess I was just kind of wondering if this picture contributes to an understanding of that limit.
In some sense, this Hamiltonian reduction is like compatible with that limit. So in the limit, you get a statement about the Hamiltonian reduction there. I mean, so the Hamiltonian reduction of like, so those things are these closed Astavas, and they call them Z nu. So the Hamiltonian reduction of this Z nu by this GA will be Z nu minus alpha I. And maybe I didn't think about it explicitly, but I think this similar statement about multiplying in the opposite direction and getting this T star C star will work there too. But,
Thanks.
So just how bad is it when you take the co-product of a Gelfand-Zetlin?
Well, it's actually not as bad as, well, I mean, these generators are like, I don't know. So if you take the generator, you sort of like want it to be, maybe not group like is the right word, but like, you want it to ideally you would get like, these generators are like labeled like, I don't know, A, I, upper S or something like this. So you'd want the coproduct to be something like AI, let me drop the lower index. So you want it to be something like AS tensor 1 plus like AS minus 1 tensor AS1 and tensor A1, blah, 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 up to AS or something like that, which just involves the A's. And you get that part, but then you get like some other stuff. And other stuff can be controlled in some sense that it's always like lower triangular tensor upper triangular.
Okay.
So in that way, we actually do have a functor from not, if you start with something in category O, then you actually get something in that's a Gelfand-Zetlin module. Because of this lower tensor upper thing, then if you're if you start with something in category O, tensor something, anyway, you can use this to do some part of trying to go between Gelfand-Zetlin modules to Gelfand-Zetlin modules, but haven't gotten it to to work in the way that we hope it should work or something. I don't know. It doesn't seem so bad, but it doesn't seem to quite work. So I don't know. I don't know what to say.
Because like, I don't know. Adding a new strand like corresponds, it has this standard filtration, which makes you think that there's got to be some sort of filtration on the coproduct that uses Isomorphic elements, where it's like upper triangular with respect to the other Isomorphic elements, but with respect to like their projections to eigenspaces and things, it's gonna be weird to write statement if you translate it over. Can't be so bad. I don't even know what happens in, like, suppose you take the Isomorphic elements of the symmetric group and take their coproducts. What do you get?
You mean just with the usual?
Yeah, I'm just doing something. I'm just curious, like what these things look like. Like,
what do you want to do with them? That's the question.
I don't know. I mean, like, it's obvious that when you take the tensor product, but
so their properties, some of their characteristic properties, you have the one in coalgebra of Sn, it's invariant under, it commutes with the action of Sn minus 1. So when you take the coproduct, you're going to get something that's going to be, that's going to have a similar kind of almost characteristic invariance property, okay, on Sn times Sn for the diagonal conjugation action. So it's a bit strange, but I don't know. Yeah, it's a good question. It must have been solved because people in the classical theory, like Vershik, Okunkov, or others, they use the justice Murphy elements. and you're asking about what really is going on for a tensor product. You take two simple representations, you have just this element acts in a very nice somehow way on each of them, and how does it act on a tensor product. So that people must have studied that in some way.
But there's no more talks today, is that correct?
Yeah, that's correct.
The schedule of this workshop's hard to keep track of the talks. Okay. Now they're speaking.
We tried to have a workshop that has the most unusual timing of lectures.
Kept moving from Princeton to Europe and then to Australia.
Yeah. Yeah.
I think you try to make sure that everybody had to get up super early in the morning to attend some talk wherever the person was living. Was that the idea?
Yeah. Particularly Raphael.
Not too bad for me. I only once to get up early, so.
But we tried to put the talks that you were particularly interested in very early. So
I noticed, yeah.
It's funny, that morning I woke up and Juan Chen had sent me all these emergency emails like, oh no, I can't get in and blah, 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 blah. And this had all happened at about 1 a.m. in the middle of the night. And of course they'd sorted it all out. But when I first saw the email, I thought, oh no, maybe there's just been no conference or something. I can smell the pancakes, so I should go and have breakfast. But thanks a lot, Joel.